talk, so as Thomas has already mentioned, we're trying to really promote our early career researchers. So at least one talk would like to be delivered by an early career researcher, and we'd also like to really represent and showcase research from scientists from underrepresented groups. So we've got a QR code here if you want to scan the form to fill out for suggestions, to suggest yourself or somebody else for future talks, or just take note of the link as well, and it's also on the email we can send around as well. So without much further ado, I'll introduce the speakers for today. So we've got two fantastic speakers which are talking about absolutely brilliant research that they've been doing on very present and relevant eruptions which have been in the public eye over the past couple of years. So first of all, it's going to kick us off. We've got Costanza Bonadonna, who I'm sure many of you will know. She's a professor of volcanology at the University of Geneva, and she's recently become president of IAVCEI. So it's brilliant to have you here, Costanza, and thanks so much for taking the time out to do this. And then we're going to go into another fantastic talk, which is on the Hunga Tonga eruption, which is by Liam Kelly, who's a PhD student at Vanderbilt University in the US. So Costanza is going to kick us off, and I'll just hand straight over, to be honest, so you can introduce your slides and go from there.
Thank you. Thank you, Alistair. Thank you, Thomas and Paul and all of you for this invitation. It is actually it's super exciting to start this series of seminars. I'm actually very happy that you're doing this. I didn't realize it was already 20 years from when we started this commission, and I'm very happy to see that the commission is still very dynamic and very lively, and it's good because there's still quite a lot of aspects in the Tephra hazard modeling that need to be addressed. So it's good to see that you have started, already just a few months after you started this new mandate with these interesting seminars. I'm also very interested in listening to the following seminar. So yeah, cool. So thank you very much. And I will start with the sharing. Okay. I hope you can see it.
Yeah, perfect.
Great.
It's fine.
Cool. Okay, so again, thank you very much for this invitation. So I thought it would be a good opportunity to discuss this recent work we have been doing on the La Palma eruption. This is a large collaborative work, and that involved many scientists from Geneva, from the University of Pisa, Manchester University, Clermont-Ferrand, University of Torino, Barcelona, and in Volcan. And if you're interested, basically I'm gonna summarize very kind of I hope, within 15 minutes, the work that you can find in more detail in these two papers that we published in JGR and then Frontiers in Earth Sciences, which is basically in the special issue of the La Palma eruption. Okay, so as you know, the Tephra eruption was a long-lasting fissure hybrid eruption that lasted about 86 days between 19 of September and 13 of December 2021. So what was our motivation to study this eruption? So first, we wanted to see what was the eruptive style of the explosive phase, and if the eruptive style actually varied with time, and there was any difference between the short versus the long time scale, how did Tephra sediment, and also how did the Tephra deposit vary with time in terms of grain size, for example, also in the short and the long time scale. So we looked at about 45, we analyzed about 45 stratigraphic section in between about 1 and 12 kilometers from the vent. So it was a fissural eruption. So basically there are multiple active vents. Here you can see these two stratigraphic sections about 1 kilometer southwest, southwest, and northeast of the fissure. So you can see they're kind of very similar. And the thickness was about 2 meters here, and then it rapidly decreased both downwind and crosswind. We could identify 3 main units and 11 layers based on grain size, color, texture, and field componentry. And as you can see here, there's a kind of a clear variation in grain size. So the lower unit was characterized mostly by lapilli size layer, the middle unit mostly fine to coarse ash, and then we went back into the lapilli size dominated unit of the upper unit. As you can see, the MDF varied between 1.1 and minus 1.8. So it was kind of started relatively kind of coarse, and then it went MU1, which is the first layer, the middle unit is the finest, and then it went coarse again. And based on direct observation, we could actually provide a timing of individual units and also selected layers. And that was interesting because then we could also more easily study the evolution of the eruption. We could compile an isopack map for the total deposit, and then we calculated the volume of the total deposit using the exponential power law and Weibull function, and the volume was about 10 to the 7 cubic meter. As you can see, interestingly, the Tephra deposit was elongated northeast, southwest. And then the volume of the individual units, so lower unit, middle units, and upper units, vary between 4 to 9 million cubic meter. And as you can see, also the units are elongated northeast, southwest. Same for selected layers. In this case, the volume vary between 2 to 5, 10 to the 6 cubic meter. But interestingly, all the units, the layers that we studied, and the whole deposit was elongated northeast, southwest. Consider that here the prevailing wind is the trade wind that blow to the southwest. We also observed a variety of sedimentation features. So in proximal areas, so meaning less than 1 kilometer from the vent, we could observe this particle-rich descending columns that we defined as lapilli waves. But then more distal area, the sedimentation was characterized by these ash fingers, which is basically which are associated with setting-driven gravitational instabilities. However, the sedimentation was in fact impacted by a variety of aspects, so like atmospheric processes, topographic aspects, and thermal feature also, because here we have consider we have a pretty large lava flow, and as you can see in this video, hopefully it will work. You can see that basically here you have the column that was dispersed over the southwest by the trade winds, but then it was also impacted by the sea breeze that was basically going inland, then by the convection of the lava flow, and by the topography. So clearly sedimentation was a lot more complex. And we also observed some particle aggregation. So here we collected the clusters on the basically sticky paper that we could use in the SEM. During dry conditions, so when there was no rain, basically the sedimentation was characterized by individual particles or quarter particles, this particle cluster 2, so PC2. However, during rainy days, we could observe this accretion pellets 3, so AP3, which is basically mud rain, we can say. So these rain droplets filled with the ash particles. And what we found, interestingly, was that even in this AP3, so clearly during rainy condition, we could find some salt and sulfur crystal, which was actually really, really interesting. It was kind of full of this. We analyzed the grain size of about 154 samples, and we could see that the total grain size distribution of the whole deposit, of the 3 units, and also selected layers, the whole unimodal, regardless of this particle aggregation and fingers and lapilli waves. And we found that the whole deposit, all the units and the selected layers, they're all well sorted with the MU1, which is basically the first layer of the middle unit, is very well sorted. As I said, this is the finest layer that we observed in the stratigraphy. But we also found that the whole deposit is really doesn't contain a lot of fine ash. In fact, if we consider F1 versus F2, where F1 is the particles less than 1 millimeter, F2 is the particles less than 63 microns, so fine ash, we can see that basically all units, selected layers, and the total deposit, they all have content in fine ash, which is less than 4%. And the activity was basically pulsatory activity. The pulsatory activity is characterized by a sequence of explosions, which is separated by intervals of about a few seconds to a few hours. So in the case of La Palma, we identified 3 main vent areas, so vent 1, vent 2, and vent 3, and then we analyzed the videos. And following the work of Dominguez et al. 2016, we can say that the repose interval, the median of the repose interval, so the log or T median, is positively correlated with the viscosity of the magma. And in order to quantify the periodicity of the pulsatory activity, the distribution of the interval, that's the time interval, can be assessed based on the log logistic parameters mu, which is associated with the frequency, and S, which is associated with the regularity. So we consider this kind of analysis, and we identify these 4 different styles. So gas buffing, which is characterized by irregular and frequent ash-pore gas pockets, strombolian explosions, which are highly regular and frequent pulses, and violent strombolian explosion, which are actually less regular and less frequent, and the lava fountains, which are more irregular and nearly continuous steady-state flow. So here we can see, for example, that for this case of the video 3, we can have 2 different styles happening at 2 different vents. So we can have for example, the violent strombolian and the strombolian style simultaneously active at 2 different vents. However, we can also have a variation from one style to another. So in this case, for example, this is the video 5, event 1, we can see that we have the variation from strombolian to violent strombolian to lava fountain in just kind of less than an hour. And we also had in the field the LPM, which is the disrometer, which is the laser precipitation monitor. And we could also analyze this pulsatory activity based on sedimentation, tephra sedimentation. And we found, for example, that for this sequence, the MD decreases with time, so going from strombolian to lava fountain at the same location, and the number of particles increases. And we also found that the sedimentation rate, as derived from the LPM, as well as the accumulation rate, which basically is derived based on the accumulation in trace, increases going from strombolian to lava fountains. We also wanted to compare the volume associated with the different products. So here you have a plot where we have the cumulative volume of lava, tephra blanket, and scoria cone. So here we divided the tephra blanket from the cone, and we found that the volume of the lava, which is about 2×10⁸ cubic meter, is about 74% of the whole eruptive volume, while the cone is about 16%, and the tephra blanket is about 10%. So clearly, this eruption was a hybrid eruption dominated by lava emission. And we also wanted to classify this eruption using different strategies. So, for example, we use this plot of pi 2000, where we can plot the magnitude versus intensity. And here we can see that all the basically the units and the total deposit, they fall in the field of these hybrid eruptions, long-lasting hybrid eruption. However, for example, the intensity in this case is constant. The total intensity, consider all the different products, is constant in time, when actually for the pyrocotine, for example, which is this great triangles, there was a variation in between, there was a variation of intensity, something that we didn't observe in La Palma. We also looked at this plot where we can basically analyze the explosivity of the eruption. This was proposed by Pioli et al. 2009. Here, the mass eruption rate of the total eruption is plotted versus it is an explosivity parameter, which is basically the ratio between the tephra blanket, the volume, the mass of the tephra blanket divided by the total mass. And here we can see that the La Palma, all in the field of the coupled system, which is very different, for example, with respect to pyrocotine, which is this red circles that can be defined as transitional system. So certainly the system of the La Palma eruption belongs to the decoupled system. Then we also use the Walker 1973 plot, where we have the dispersal parameter versus the fragmentation parameter. In this case, we can say that the units and the total deposit, they all fall in the Van Strombolian field, according to this plot. So to conclude, we can say that the 2021 Taucarite eruption of La Palma was a hybrid eruption with about 74% of lava, and was characterized by multiple active vents associated with different eruptive style. So we have lava flows, and then we have explosive eruptive style, and these explosive eruptive styles were analyzed statistically, and we could say, so this is basically in the short time scale, we can say that there was a rapid variation of gas flux, which modulated the transition from the bubbly regime, which is basically the gas puffing, to slag, which is the Strombolian, to charm, which is the Van Strombolian, to annular flows, which is the lava fountains. And this happened at the same vent or multiple vents that were active simultaneously. And we can say that the eruption classification based on deposits, so basically over the long time scale, basically indicates a decoupled magma gas system with the Van Strombolian explosive phase. But overall, we could observe a relatively constant cumulative mass eruption rate during the eruption, based on this intensity index plot. We could identify 3 stratigraphic units, lower, middle, and upper units, subdivided into 11 layers and 18 sublayers, which were identified based on color, grain size, and componentry. We found that the total deposit, as well as the units and the layers, were elongated northeast, southwest. So as we said, the trade winds basically they blow towards the southwest, but basically the whole sedimentation was affected not only by the trade winds, but also by the daily land sea breeze and the convection induced by the lava flow field. And the volume of the total tephra blanket was estimated to about 2×10⁷ cubic meter, even individual units between 4 and 9 million cubic meter. Finally, we can say that the pulsatory activity plus this variable eruptive style in time caused short time variation of tephra ground accumulation rate and grain size. And the sedimentation was characterized by various features, including lapilli waves in proximal areas, ash fingers in medial and distal areas, and particle aggregation, mostly coated particles during dry days and liquid pellets during rainy days. And we also observed very well sorted to well sorted unimodal grain size distribution and total grain size distribution with a very low fine ash content, less than 6%, considering all the different samples. With that, I finish and I thank you for your attention. Of course, I'm happy to take any questions.
Perfect. Yeah, thanks so much for that, Costanza. That was a fantastic talk. That's really, really brilliant. Great to see all those amazing photos in there as well as those really cool lab graphs. So thanks for that. Has anybody got any questions? Yeah, just raise your hand or just pop up. Can't quite see everyone yet. Oh, Ben, I can see you've got your hand up. Go ahead, ask away.
Hi, everybody. Hi, Costanza.
Hello.
Thanks a lot. How are you?
Good. Nice to see you virtually.
Thanks. I don't have a camera.
Yeah,
but,
I don't see you, but I see the BB.
Very, very interesting work. And I saw that there were lots of people on the field. And I was wondering, how do you did some homogenization of the observation of the different stratigraphic columns because there's so many.
You mean from the different people?
Groups or people or yes.
Yeah, well, actually, so we work together. So basically, for example, and the groups were like separate in time. For example, like Jorge Romero from the Manchester University, he was there in the first part of the eruption. So like, let's say more like in end of September. And basically that work went into his paper that characterizes the first part of the eruption, and his observations were like super important for the definition of the timing, because then we went later on and the timing of the eruption would not be possible without the direct observation. So basically we could compare, for example, all the different pictures, and we could compare, you know, the timing, because some layers were very unique, you know, were very kind of for example, there is this MU2, which is characterized by this red lithics and red, let's say, oxidized scoria. And then all this observation could help us provide the timing. And then, of course, the Involcan was their work was very important because they had this tray network that also helped the characterization, you know, the comparison between what fell into the trays, even though the collection was not done obviously like daily, because of course, you know, people were like super busy. But then, you know, they had like, we could compare the layers with what was in the trays of this of Involcan. So this is why it was kind of really, really important. But then, of course, the different groups, they contributed in different ways. For example, like the lava flow characterization was done by Diego Coppola from the University of Torino. So anyway, so let's say different groups contributed in different ways, and that was this is what makes this study particularly, for me, special, because it's very multidisciplinary and we needed all this different expertise coming together. And then, of course, it was very important to have the support of Involcan that was there basically during, of course, I mean, during the whole eruption. They could manage all these different groups, and they provided absolutely precious support during the eruption in terms of like logistics and also like what they did, which was very important, is really to put together this lithoteca where you can find basically samples, and then eventually people will be able to access it. So they did a fantastic job into this collection of samples and ash samples throughout all the eruption. So I really think they did a fantastic job in that respect.
Oh, that's brilliant. Yeah, thank you. Has anybody else got any questions? I'll try and swap between the chat and the.
I will ask one in the meantime, if that's okay.
Yeah.
I'm sorry if I missed the slide, but you mentioned ash sedimentation being affected by convection from the lava flow.
Yeah.
So how did that translate? Was it essentially delaying convection? Because
Well, I mean, as you see,
flow, or?
It's kind of interesting. I mean, we don't really. I mean, of course, it's kind of difficult to see the signature of that in the deposit, but we could actually observe it. So we could observe all of this kind of happening. And this is why, so the convection somehow was delaying the sedimentation of the ash. It was and somehow you had this kind of combination of this convection from the lava flow. And then what we think was also particularly important is this sea land breeze, which somehow was was combined with this prevailing wind towards the southwest. But then also there were these days when the trade winds were absent, in which case basically the wind could rotate 180 degrees. So basically this is why also you have this interesting elongated deposit northwest and southeast. And this, what I found absolutely striking, which I didn't expect, is the fact that basically the deposit southwest and northeast, they mirror each other. So you really find exactly the same units, southwest and northeast, which I didn't expect, because I thought, some units went to the southwest and some units went to the northeast. And actually you can find exactly the same units in a kind of in the same place, like in both areas, which I think this is why we think probably that the sea land breeze that kind of acts every day could actually have an important effect. But talking also with Arnaud Folk, that is also involved in this work, all these complications also affect a little bit the daily forecasting, of course, especially for this kind of proximal areas. Because of course, then not only you had that, but you also had this kind of very fast variation in plume height. Because I mean, of course, you had multiple vents active, and then you had multiple erratic styles, so the height varied very rapidly, which was something that really affected the daily forecasting, which was a little bit complicated.
Cool.
Yeah, that's great. And I think we've got time for just maybe one more very quick question. So so Jess, I can see you got your hand up. So yeah, feel free to ask.
I was just wondering how this compared, like the patterns in the deposition compared to previous eruptions, in the sense that were those winds making the same sort of patterns in maybe like the 1991 eruption and stuff like that? Did you look into that?
Well, I mean, let me just share. I'll just try to share it again. Just want to show you something, because it's interesting. Let me go back here. Yeah. Can you see it?
No,
No.
it's
No.
not shared, I think.
Okay, let me share it again.
Perfect. Yeah, I can see that.
Okay, so basically here, what we wanted to see, as you said, I mean, it's like, how does that compare with previous eruption in La Palma? So here you can see the Teneguía eruption, the 1971, which is this pentagon symbol. And this is basically was the previous eruption and on La Palma. And that one was plotted by Walker himself in his paper, and that fell into the Strombolian field. And in fact, that was certainly a lot smaller eruption. I mean, it lasted for about months, but also this is a picture also of this eruption, and it also happened on the, let's say, the vent. The cone was close to the coast, and it didn't really affect a lot of houses. I mean, and so that one was considered more like a touristy eruption, let's say, because people went to look at it, to watch it. there were a couple of casualties, but were mostly related to people going too close. I think they were affected by the gas actually, but really didn't really affect the island very much. But also was a lot smaller. So this one for sure, in terms of the explosive phase and in terms of the Tephra deposit, was massively larger, for sure. I mean, both were hybrid because, of course, also let's say this one was, I mean, the Tenegia eruption produced both lava and Tephra. However, the explosive phase was a lot less intense and less, let's say, didn't last for that long. So this is why it also, in terms of the management of the eruption, was very tricky because, of course, people didn't know what to expect, because, I mean, they thought, maybe it was kind of something similar more to the Taucate eruption, of course, so the Tenegia eruption. Of course, also the location, when you have this eruption, these monogenetic fields, the location, of course, is fundamental. So like the Tenegia eruption that happened on the coast, of course, the associated impact is going to be very different compared to the Taucate eruption that happened in the middle of an populated area. So from the beginning, that created an issue. There was a problem, of course. But in terms of just from the volcanological point of view, regardless of the location, the Tenegia eruption was also smaller.
Fantastic.
Thank you.
Yeah, thank you very much. Yeah, thanks again to Costanza for a fantastic and fascinating talk. That was absolutely brilliant.
Thank you.
So yeah, so I'll swiftly move on to Liam's talk. So Liam, hopefully you're there. Oh, there you go, pops up. So yeah, so I'll just hand it straight over to you because we've done the introduction. So yeah, go ahead whenever you're ready. Thank you.
Thank you. Great. Yeah, thank you to Alistair and Thomas and Paul for organizing this and for the invitation. And thanks also to Costanza for a really interesting talk. So I'm introduced, I'm Liam Kelly. I'm a PhD student at the Vanderbilt University here in Nashville, Tennessee in the US. And I'm going to be talking about work that I've been doing to try to estimate the airfall volume of the 15 January 2022 eruption of Hunga volcano, mainly looking at how that relates to changes in ocean color. This kind of came out from a side project that I started during my master's where I was looking at the impact of a different eruption on the ocean color and how that kind of related to different things in ocean biogeochemistry. And when this eruption began, we got interested in, can we try to utilize the methods that I've been using for my master's to try to think about the volume of ash that's deposited into the ocean. So this image here is just showing an eruption from Hunga volcano, actually a day before the eruption that I'll be talking about. But you can see that there are islands on either side of the Hunga volcano. It's a submarine volcano. The vent is generally located below the surface, and you're having this intense activity of ash ejecting from the submarine vent and then deposition of ash into the ocean. And so the January 15th eruption was a very large submarine eruption with plume heights that reached about 55 to 58 kilometers, some of the highest that have ever been recorded. And because it's a submarine volcano in relative open ocean, most of the ash was deposited over the open ocean. And you can see these outlines here in blue are outlines of different islands in the Kingdom of Tonga. And so there is some ash deposition onto the different islands, but the majority of the deposition of the ash occurs over the open ocean. So when thinking about what is motivating this work and the questions that got us excited, the first question is what is the volume of ashfall from this eruption of Hunga? And then the second question kind of goes into the first question a little bit, and that's, can we use remote sensing to measure ash deposition volume over the open ocean? Can we try to develop some sort of new method that thinks about the impact of this eruption on the ocean to the actual volume of ash that is deposited? So when we think about the ocean and we look at what's going on in the ocean, an image here on the left is from January 17th, 2022. So this is 2 days after the eruption of Hunga volcano. And you can see Hunga volcano here with this red triangle. And you see this kind of greenish, light greenish blue area of discoloration in the ocean versus your traditional darker blue color that you expect to see in an ocean like this, just kind of highlighting it here. And so we have this response in the ocean after we have this really large eruption where we have ash that's being deposited. So the goal is to try to draw some sort of relationship between the discoloration that we're seeing here, as well between the discoloration that we're seeing here and the eruption that happened 2 days prior. So before I go any further, I kind of want to establish some context on how I'm thinking about discoloration in this context. And so I'm really thinking about discoloration from particulate material. And if you were at IAVCEI or heard about what happened, you know that there was very intense rainstorms that were happening during the week and before of IAVCEI and delayed some flights. My bag got lost in the Cook Islands for like 5 days. But what happened here is that you can see where we have this increased raining events. We're having this runoff into the ocean. This is an image from Hawke's Bay on the eastern coast of the North Island of New Zealand. So we're seeing this similar discoloration that we're seeing in the ocean after the eruption of Hunga volcano. And this is the deposition of particulate material into the ocean that is really causing this discoloration. So runoff from the coast can cause it like we're seeing here, but we are also now assuming that ash deposition could possibly cause the same response in the ocean around Hunga volcano. And so when we're thinking about the deposition of ash into the ocean, we're really interested in the fallout of ash from the plume. And when you look at satellite images, if you recall the images that I showed towards the beginning, you're really only seeing the plume from the top down, and you can estimate volume based off of the eruption rate here, but I really want to understand the amount of ash that's falling out from this plume, and this is actually hidden in the satellite imagery generally, especially with a plume like this, which is mostly radial. You're not having any directionality to this plume during the initial pulse of the eruption. And when you look at the satellite data, what you see in the images is that the plume is majority composed of ice and water vapor particles. So you're not really seeing a large contribution of ash in the plume from the remote sensing data. So we're focused in the deposition of ash from the plume into the ocean that's hidden by the actual shape of the plume in the satellite data. So we want to have some sort of proxy. So we're using discoloration as a proxy for ash deposition. So we have this, we know that there's some deposition of ash happening in the ocean, but how do we think about this discoloration in relation to ash thickness? And so, like I said, there was some deposition of ash onto islands in the Kingdom of Tonga. And you see here images from Nuku'alofa. This is just an aerial image of some houses, as well as an image of ash on top of a car. So we are having deposition of ash onto the islands of the Kingdom of Tonga. So we have some sort of measurement of ash thickness from this plume at certain locations. And so we want to find a way to relate this thickness of ash that we can measure on the islands to the discoloration of the ocean that we observe in the imagery. So just as a reminder, here is our image showing discoloration in the ocean. Here is Hunga volcano in the red triangle, and we're having this area of discoloration, this greenish color that is kind of similar in color to the images that I showed from Hawke's Bay in New Zealand a couple slides ago. And so we want to extract some spectral information, so quantitative information about this image, and then find a way to relate that to thickness of ash that we have measured on these islands. So the first part of that is obtaining the spectral information from the image. So the way that we did that was we used a satellite product, the Modus Aqua surface reflectance product, which is freely available on Google Earth Engine. I'll talk about Google Earth Engine later towards the end of the talk. But this is atmospherically corrected, so you're not having any impact of aerosols in the atmosphere on the image that you're seeing in the ocean. And so if we look here, this plot on the left, we have reflectance plotted versus just the wavelength of the different bands that the sensor is sensitive to, we can see that we're seeing large increases in reflectance for the green and blue band wavelengths. And here is the blue band, here is the green band. The three curves show two different discolored areas, as well as one area that does not appear to be discolored. So in the curves where we are looking at discolored water, we're having this increase in reflectance at these two wavelengths. So and then I got to thinking, how can I actually create one mappable value from this spectral information that I can then try to map to ash thickness? So what I decided to do is, since I saw this marked increase in both the green and blue bands for discolored areas, I decided to average the blue and green wavelengths to get a single value of reflectance intensity for each pixel in my image. So now I have something that I can directly map to ash thickness. The next thing that we need to do is, if you look at this image again, this is just showing the same discoloration, but now just showing a little bit of the ash plume, as well as these three boxes, which these three boxes correspond to the three curves in the plot to the right here, where you have your different discolored areas. You can see kind of qualitatively the difference, that there are differences in color and appearance that's reflected in their spectra, as well as out to the west, we have a box that is just showing where there was no discoloration. And if you look at the image, the first thing that you see is there's a decent amount of cloud cover. The cloud cover is actually blocking the color of the ocean. We're interested in what the ocean is looking like. We're not really interested in the clouds here. So we have to find a way to mask out the clouds. So we mask out the clouds from our image. And then you also see in brown here are different islands in Tonga. And where these islands are located, we do not have ocean color present. So we want to remove these islands and then find a way to interpolate our reflectance over the missing areas where we have clouds and where we have islands. So we want to generate some sort of image that has reflectance over the areas where there are clouds present, as well as where there are islands present. So we can equate ash thicknesses on islands to a certain ocean discoloration that we can calculate here. So we interpolate to try to get a big image of just the ocean reflectance interpolated over all these gaps, and we interpolate roughly over the umbrella cloud area. So now we have an image of where every pixel is some sort of reflectance intensity. But the next part of the question is, how do we think about this in relation to the ash thicknesses? So the first thing that needs to be done is that ash actually has to be sampled and thickness has to be measured. And so the sampling was done by some of my collaborators that were able to get on the ground in the Tonga Geological Services and from the University of Auckland, as well as others and community members on different islands in Tonga. And the sampling was done days to months after the eruption, depending on the location, and multiple locations throughout the Kingdom of Tonga. And you can see the island down below with all of these purple points is the island of Tongatapu, which is one of the larger islands, and it has the capital of the Kingdom of Tonga, Nuku'alofa. And so we have the most points on this island here, and then we have some other points on different islands. So now we have all of these samples, or all of these different ash thicknesses and different locations on different islands. We have our image of reflectance, where every pixel corresponds to some sort of intensity value. We want to figure out a way to, again, link the ash thickness to the surface reflectance. So what we end up doing is we take an area of our reflectance image that is centered on our ash location, and we can take the average of this area of reflectance, so we can get some sort of value for reflectance that we can then equate to the ash thickness that is present at that location. For example, we see an example here in the bottom right. We have an ash thickness from our point, we have a reflectance from our area, and so we try to equate ash thickness to reflectance. So we do this for every single sample that we have. We have all of the locations. We have the same size area around every single location, and we average reflectance over this area to get the average, as well as some uncertainty in reflectance. And then we use this to calibrate our reflectance to our ash thickness. So now we have pairs of data where one dimension is ash thickness, the other is reflectance. And so then we are able to generate this figure with ash thickness on the y-axis. You can see we'll call that H, and surface reflectance on the x-axis, we'll call that R. All of these different points are our different samples with their corresponding ash thicknesses and reflectance averages. The error in the ash thickness measurements are 0.5 centimeters just from when the samples were taken. And then you also see that there's this error in the surface reflectance. So what we noticed is that as ash thickness increases, surface reflectance also increases. So we decided to just draw a simple linear relationship between ash thickness and reflectance. You can see here up in the top left, it's a very simple equation that we use because our goal is to just create a calibration of ash thickness to reflectance. So we run a linear regression on our whole set of data points to obtain some sort of linear relationship where we can then map the surface reflectance values that we have in our image to a certain ash thickness. So the result of doing that procedure is what I've termed an ash thickness map. And so this ash thickness map, you can see on the left here, the contours are in 10 millimeter increments. Closest to the vent for Hunga volcano, you're seeing we have the highest grain sizes present. So we can calculate the volume off of this by just adding up all of the different ash thicknesses in our entire ash thickness map, and then dividing by the whole area of the ash thickness map. And by doing this, we get an estimated airfall volume of about 1.7 cubic kilometers. The range of porosity for these samples gives dense rock equivalents of about 0.34 to 0.71 cubic kilometers. And this volume, important to note, is that this volume is a lower bound. It's mostly taking into account reflectance that's closest to Hunga volcano. So it's possible that there is it is larger, but we have a lower bound now for our ash airfall volume. So there's some possible sources of uncertainty that we can have in the reflectance. The first is that large particles that are deposited closer to the vent are likely underrepresented in our analysis. We don't have any ash thickness measurements from areas closer to the vent on islands because there's not islands that were sampled for ash thickness closer to the vent. And so the larger particles are going to sink more quickly in the water column. They're not going to have as much staying power as the finer particles. There's also this possible influence from the coastal erosion, like I showed earlier from Hawke's Bay, but due to the scale of the discoloration after the eruption, it makes the coastal discoloration kind of undistinguishable. And so I don't think that that's having a large enough impact to cause problems here. And then there's also the movement of ash that can occur due to ocean currents. And I think that, again, this is from January 17th. The eruption was on January 15th. So I think that could possibly be lending to this kind of southeast extension in the ocean color imagery that we see here. So when we think about the relationship of our volume and the discoloration to the umbrella cloud, you can see here, this is a snapshot of the umbrella cloud about less than an hour after the eruption. And then if you are familiar with the eruption at all, you know that most of the intense activity happened within the first hour, and then the plume kind of was advected away from here. And so when we look at the snapshot of the umbrella cloud, we see that it's larger than the extent of the discolored water. This suggests to us that much of the ashfall was deposited within 100 kilometers of Hunga volcano. Our smallest measurement of ash thickness was about 250 kilometers away, of about 1 millimeter. And so our ash thickness map that we've created in line with the discoloration agrees with the idea of fallout of most of the ash closest to the vent. And so now when we think about the volume estimate of that we've calculated in the whole context of the eruption, the estimated volume change from the subsidence of the caldera, as well as material that was removed from the ocean floor, is calculated to be about 10 cubic kilometers for the total eruptive volume. So our calculated airfall volume, whether the dense rock equivalent or the non-dense rock equivalent airfall volumes that we've calculated, represent at least less than 20% of the entire total volume, possibly less than 10% of the total volume is from airfall deposition of the ash. And so the submarine deposits seem to be dominated by density currents and not really by our airfall volumes. And so even though the airfall is maybe a smaller proportion of the entire volume of the eruption, the value that we've calculated of 1.7 cubic kilometers is consistent with other estimates for the airfall volume that are integrated from data of the plume height. So what we are finding is in agreement with what others are finding as well, with different methods. So there's also been talk about this discoloration that we're seeing in the ocean being a possible phytoplankton bloom. And there's been two different kind of papers that have come out about this. One paper interprets this discoloration as increases in chlorophyll and chlorophyll fluorescence that relate to a phytoplankton bloom that was triggered by ash deposition. A different paper came out months later that disagrees and thinks that the ocean spectra is not really in line with the chlorophyll and fluorescence increasing that you're seeing in the ocean. But for us, this is not too important what the interpretation is of this discoloration, since we are directly working with the ocean spectra, versus chlorophyll is actually, it's a derived product from the ocean spectra, just like we have derived our ash volume or our ash thicknesses from the ocean spectra. So our calibration is still valid if you interpret this discoloration as chlorophyll. And you could also calibrate to chlorophyll concentration if you like, because you're having this being triggered by ash deposition. And this is an active research area. I actually worked my master's on an eruption where we are seeing ash deposition possibly triggering phytoplankton blooms. That will be out soon if you're interested in more of this work. And so this is still something that's going on, and with the more satellite data that we have, we can think more about the impact that eruptions have on the ocean biogeochemistry. So just some takeaways to finish up. The first is that this method can be used to obtain eruption volume estimates using a tool that's free to everybody with little overhead or processing required on the part of the user, Google Earth Engine. Once you have measurements of ash thickness, you can calculate an ash volume relatively soon after that. And this is a new method for estimating airfall ash over the ocean by relating ash thickness to discoloration. In the ocean, we are able to estimate an airfall ash of about 1.7 cubic kilometers, which is 10 to 20% of the total volume of the eruption. Thank you again to my collaborators, and thank you to all of those who helped with the field data collection, our funders. There is a preprint out of this work. It's currently in review at the Bulletin of Volcanology, but there is a preprint. If you'd like to read it, you can scan the QR code here and either ask me questions now, or I'm happy to talk at a different time about this work as well. So feel free to email me. Thank you.
Thank you so much, Liam. Fascinating talk and pretty cool new methods to reconstruct the deposits. So, do we have any question from the audience first? I realize we're running a bit late. I blame the fact it's our first seminar, but yeah. Do you have anywhere to go, Liam, or are you able to stay a few minutes? Okay.
No, I'm going to stay.
I have loads of questions, so
Sure.
I could go on forever. So yeah. I guess I would just start with one, and then we'll see if there's one. So the scaling you pick at the moment is linear. I guess the exact scaling is going to depend a lot on like what type of eruption, maybe what type of ocean, or the local chemistry, or the satellite instrument even. But do you think that linear scaling should be something robust and applicable to other eruptions?
Yeah, I think so. The way that we understand the relationship now is I haven't seen any other indicators that the relationship between ash thickness and reflectance is not linear, because when you think about what's causing this reflectance is when you have more particles in the water, you're kind of like increasing the amount of scattering of the light, which is then increasing kind of the reflectance. So my hunch would be that this linear relationship can be broadly applicable, but like you said, depending on the conditions of the ocean, that might change. And also, like, I did multiple days, not just January 17th. So I found that this linear calibration on multiple different days kind of gives ash volumes that are similar. But as time passes after the eruption, the reflectance signal kind of like breaks up and as well as decreases. But it can also kind of depend on the angle of the sun as well and how much the sun is impacting. So that could also be something that needs to be taken into account in like future iterations of stuff like this. But I think to get a first order understanding, especially like close after the eruption, the second that you get some sort of ash thicknesses, you can make a quick estimation of the ash volume. My first estimate I had was about maybe two to 3 weeks maximum after the eruption, when I just received 5 ash thicknesses, and the answers stayed relatively consistent, depending on how many points I used either. So it seems to be relatively consistent, but there are definitely other parameters that you could look into and see how those could impact the different calibration.
Cool. Any question from the audience? Okay, I will throw another one quickly then. Sorry, I don't mean to monopolize, but about the you know, you made the point that you don't have distal measurement, or that, you know, it's a minimum volume estimate. Could you use some of like the standard, well, could you use your measurement to start building a thinning trend curve and kind of extrapolate using some of the standard methods used by field volcanologists, like Costanza mentioned the variable function, the exponential function, and test these different methods, and, you know, maybe try to at least get a range for the distal part?
Yeah, no, that could be, yeah, that could be definitely something that could be done, and something that I would be interested in seeing. And like, how can we now, thinking about like trying to do something that's reminiscent of like the traditional methods of estimating ash volume and like ISOPAC maps. And so trying to like do some methods that are closer to that traditional approach, I think could be relatively beneficial to try to get at the distal stuff. Because once the discoloration and the reflectance value hits a certain point, it's not as much use, I would guess, to kind of equating to ash thicknesses, especially as it thins more and more. The impact that it's going to have on the reflectance is relatively minimal. When we had the smallest value of about 1 millimeter, the reflectance was, I guess, half of the amount from the smallest value to the values in that we were seeing and mostly using to calibrate. So I think that kind of extending it and going towards using these more traditional methods for estimating could be useful to kind of get that sense of the distal amount.
Okay, amazing. I think, you know, I think both Alastair and Liam are happy to stick around, but maybe first of all, let's thanks again both Liam and Costanza. I think Costanza has gone in an IAVCEI meeting, so she left already. Also, I noticed a couple people arriving just now. Sorry again for the time change last week, and sorry that you missed the seminar. So if you have more questions for Liam, yeah, you can keep asking them. Also, if you have suggestions for the Tephra Hazard Modeling Commission, if you want to let us know what you thought about the seminar, please stick around and talk to Alastair, because I'm about to go. Or also you can just email us. So yeah, Alastair, I will let you take the lead. I'll just put up the slide again with our link to sign up to the commission. Or I guess you should. Yeah, well, yeah, it's
got it actually, haven't I?
If you have the slides, you can put them up. Yeah. Thanks again for joining. Sorry for the messy organization, and thanks for sticking with us for this first one. And again, if you have questions for Liam, go ahead. Yeah, thanks, Liam.
Yeah, thank you.
Yeah, thank you. Great. Hopefully everybody can see that. Although I kind of lose everybody else, so I don't know if I'm talking to a room with lots of people there or a room with not many people there. But anyway, thanks, Liam. I can see you. You're the person I can see. So if you stay on and let me know if everybody's gone, that's great.
Yeah, sure.
But yeah, so hopefully that's hopefully, I mean, thanks again, Liam, and to Costanza as well for fantastic talks, and hopefully you've enjoyed them, and hopefully everybody else has enjoyed listening to them as well. I certainly have. They're brilliant talks to kick us off with this. So just to kind of throw it out there really, I guess, as a post-talk discussion, just for 5-10 minutes, just some directions here about whether you like the talks, whether you like the format, if you've got any comments or suggestions about them, any more science chat about the talks or any other topic that anyone wants to raise. And then just generally kind of things about commission activities. So what would you like to see? How can we support you, basically? So we'd sent around earlier to those that aren't members, to members probably a couple of minutes ago now, we'd sent an online form which had these sort of questions on there. We've got the feedback from that. We're trying to take those on board, but it's just a good space to kind of get everybody together and to basically hear directly from you. And then the final one, if there's any appetite for training courses, online modelling workshops, or Tephra Hazard modelling led field trips. So I'll leave the slide up a little bit, and then I'll probably just stop sharing the screen, just so people can take down the QR codes and the links and stuff. But yeah, feel free, just shout out, because I can't see anybody, unfortunately, apart from Liam. So yeah, I'll open the floor up to anybody to say something if they wish to. It's quite quiet. Is there anybody left, Liam?
It looks like there's 4, but
4. Okay. Yeah. Right, I'll stop sharing the screen, and I'll just see how everybody's. Cool. Yeah, people might have just popped off anyway. So
yeah, no, for sure. No, thanks. Yeah, this was really great, and looking forward to coming to more of these. It's kind of, and haven't really been plugged into this Tephra Hazard modeling like community before, so it was good to kind of see like what it was about, and trying to think about like what is the stuff about that I'm working on, like trying to link that with the audience. So it was really, really great, and really appreciate the organization and the invitation. It was awesome.
No, that's great to hear. I mean, yeah, thanks so much for accepting it. I mean, it's I mean, we just it's our first one, obviously, and we just tried to think of different ways to kind of get the community together. I think particularly since COVID, like, a few commissions have done online talks, and it's been a really good element of that, where we've brought across an international community together in one space. And obviously we're going to try and do things a lot more at conferences as well. Yeah, we've got a few ideas basically lined up for coming over the next sort of year or so. Unfortunately, COV, I think all of us can't attend. I'm trying to work on getting some funding, but for IAVCEI, I think we'll try and do something there. So one of the things that we're trying to do is set up a field trip as well. So the previous commission leaders they're all set for a field trip to Santorini, and then that was right in the midst of COVID. So that all fell apart. So I think we're trying to work on something that maybe to Etna could be quite cool.
Yeah.
But I mean, just while I've got you, I mean, don't feel like you've got to stay and be roped into it. But I mean, what are your thoughts on that? Like,
I mean, I personally, like, I always jump at opportunities to go into the field, especially because most of the work that I've done has been kind of like on the computer for most of my career and stuff. So like, I love going into the field. So I'm very interested in kind of learning a little bit more about thinking about the hazards, and like going to actual volcanoes and kind of thinking about that. So I mean, definitely am interested if the opportunity would arise.
Awesome. That's great. I can see Jess has just put a hand up, and I've just seen your comment in the chat. So would there be an interest in student outreach? So what do you kind of mean by that? Are you able to elaborate on that a little bit more?
So I'm currently doing a master's at Bristol, and I was part of the Geology Society, like our society at uni before that.
Yeah.
And I know we're trying to maybe focus a little bit on having some academic talks, and I was wondering maybe if the commission would be interested in getting involved with something like that, and also if it would be possible for basically just any sort of student involvement would be good, because I know quite a lot of people would be interested in that.
Yeah.
And I know a lot of the people on the volcanology course, well, I mean, there's only like 7 of us, but most of us would be interested in that as well.
No, exactly. That's great. Yeah. So I did when was it? It's 2016 to 2017. I did the master's course at Lancaster, so the other one other than Bristol. Yeah, we kind of knew all of the people who were on the Bristol course. So I totally get that. With a small group of people that, you know, trying to find a space. So I don't know if you know about IAVCEI ERC Net. So it's like the early career researcher group. So that's a really good group, first of all, to kind of have like a community of early career researchers to kind of be part of. But yeah, I think that's definitely something we're really interested in kind of promoting. I mean, we're all early career ourselves in this new leadership team. So yeah, we're really open to kind of, you know, at least promoting research, or, you know, trying to facilitate, you know, sort of science and science engagement with early career researchers. So I think definitely if you've got any ideas for things with that, that'd be great. But I mean, for personally, I think, you know, I'd be quite open to, you know, sort of showcasing, you know, whether even short talks on what people are being involved, their projects are involved in. You know, I mean, it's you know, you all have a dissertation topic later in the year, and that, you know, many of those often go on to be publications, or, you know, sometimes get lost in terms of just being a thesis, and nobody really knows who's worked on different things. So I think it's a really good way to kind of, first of all, introduce yourself to the community, and second of all, for the community to kind of get to know you. So I think yeah, I mean, I'd be very open to that. I mean, we've got obviously lots of different commissions across IAVCEI, so some talks might lend themselves to other commissions. So it might be, you know, a commission on glacier volcanism, or the commission on explosive volcanism, or, you know, whatnot. There's lots of commissions, or volcanic gases, and we're kind of primarily, you know, kind of down the Tephra hazard modeling route. But I mean, this kind of this commission kind of encompasses a, you know, a wide variety of volcanologists, really. I mean, I've sort of come from a field background. Thomas has come from sort of climate background. Paul's more of a modeler. We're looking for experimental sort of volcanologists to be more involved than they used to be, because that's a very important part of what we're doing. So I think that'd be brilliant. And yeah, if there's things that we can support with directly towards master's courses as well, or kind of groups, or even if it's just you know, whether you take on a lead of kind of sharing, you know, the commission website with everybody in your group, and getting them to attend, you know, the next kind of quarterly seminar, and they kind of get involved, we can sort of try and facilitate that, and kind of say, here's the Bristol group or whatever, and all of that. So hopefully
that would be awesome. If I could maybe send you an email.
Yeah,
I'm not currently, and then maybe I can CC maybe society. I don't know how much undergraduates would be interested in it, but definitely the master's students. And I know we're trying to get a lot more postgraduate students involved with the society itself. But even apart from that, just the volcanology group, I think that would be maybe really exciting opportunity to sort of explore.
Yeah, no, that's brilliant. Yeah, definitely shoot me an email. Have you got my email address, or have you got it from the website, or
I don't. I did just, I think I added you on LinkedIn.
Okay, cool. Yeah. I'll pop it in the chat as well now, so you can just take it down as well.
Okay, amazing. Thank you.
Okay.
Head out. Thanks so much. Have a great day.
Yeah, thanks so much, Liam. Yeah, it's really great talk, and yeah, speak to you soon. Yeah.
Yes.
Thanks. Have a good one. Thank you. That's brilliant. So Lucia and Nicola, are you still there at all, or have you gone? Okay, they've gone. Okay, so I think it's just you and me, Jess. So
Okay,
yeah, I mean,
sorry.
no, that yeah, definitely shoot me an email about that, and I can try and, you know, sort of send things over to Paul and to Thomas as well. We've also got yeah, we sort of have like, we don't often have like discussions with the other leaders, but we kind of email to each other, and we're involved in some like IAVCEI emails as well. So if things lend themselves better to other commissions, we can kind of facilitate that as well. But I think it'd
Yeah,
be
for sure.
brilliant, because we
I
yeah,
mean-
yeah, go ahead, sorry.
Sorry. I mean, this itself was advertised. Sam Mitchell sent an email around.
Right, yeah.
So I think that's maybe the link to Bristol through this.
Yeah.
But I think it would be something that a lot of people
Right.
would be interested in.
Yeah.
And especially the other areas as well, because I know we've got quite a lot of keen petrologists on this course at the moment. So
Yeah, no, exactly. Yeah, there's a quite a large commission called the VIPS, which is like the volcanic igneous swimming, or so, you know, it's it's basically more geared towards petrologists. But that's the thing, like over the past, so basically commissions, I think there was, from the way I kind of understand it, it's about 20-30 years ago, like the commissions were quite active and they were quite new things. And some of them just kind of fell off and died a little bit. And some were kind of kept alive, and some merged together, and then some had a leadership that weren't very active and whatever. So THM's kind of always been quite active, but it's yeah, I think we're always trying to, every new leadership that comes in tries to reassess kind of what's going on. So we've got different working groups. We've got a working group on the IVESPA working group, which is looking at eruption source parameters, and we've got a working group that's looking at ash aggregation. The IVESPA one is really active, and it's got publications coming out all the time and things. And the ash aggregation one's pretty inactive, and you know, and that's really like when you look at Tephra hazard modeling, the state of play at the moment. The ash aggregation one would be really useful to kind of kick back up. It's like a really important
absolutely
thing to kind of bring back in. Like there was a lot of ash aggregation studies years ago, and then, you know, it kind of seems like a lot of the modelers now kind of think it's all been done, but the field geologists don't really agree with that. So we're kind of looking for people to kind of lead on these working groups and stuff. But also like just any sort of new ideas. Like we'll try and have a big presence at the IAVCEI conference in 2025. And we'll try and run this field trip as well, like I say. We've got ideas for like modelling workshops. So to try and introduce people just to kind of, you know, how to run a model and how to simulate different eruptions. Like that's stuff that as a field geologist, I didn't particularly know until recently, and I still don't know very well. So just having people that kind of, you know, lead these workshops, which are, you know, brilliant things that then you can integrate into sort of master's projects, or, you know, just kind of running. So I mean, like you'll definitely run models in Bristol. There's like the plume lines and the, you know, all of that. But like, you know, introducing different things. Exactly. Yeah. So yeah, so I think it's great, and like, yeah, it's brilliant. Sam's sent that around. I know Sam quite well, so he's yeah, it's brilliant he's sent that. And yeah, I mean, are you a member of the commission at all, or
No, this is my first meeting. I was just quite interested.
Yeah.
That was all.
No, that's brilliant. So if you enjoyed it, just go to our website. I can put the link in the chat again. And you can just sign up literally at the bottom of the page. It tells you what to do. And
yeah, I'm part of the mailing list. I don't know if that's the same thing.
Yeah, that's the same thing. Yeah,
that's what it is. Okay, cool.
That's it. Yeah. So it's great if you're on the mailing list, and you've got my email now. So just just shoot something over, and we'll see what we can do. Because
okay, cool.
Yeah, because I mean, it'd be maybe a really good thing to try and integrate with some of the other master's courses that are either in. So it's like the UCL one, is the Lancaster one that I did.
Yeah.
But also like the groups that are overseas, like in Clermont-Ferrand have got a big group, or Munich have, you know, sort of big group. So we could try and maybe facilitate something across all those different groups as well, and then you get to meet other master students that are working like, you know, in a different university on the same thing, that have got a similar size cohort, similar group, you know, because you'll eventually bump into each other down the line. So Yeah.
Yeah, well, I hope so.
Yeah, exactly. So no, that's brilliant. And yeah,
Cool, perfect.
hopefully you're enjoying the course as well. So
Yeah, I am definitely.
that's brilliant.
But yeah, thank you.
Cool. Yeah, no worries. Yeah, thanks so much for coming, and hopefully see you again at future ones.
For
So,
sure.
yeah.
Okay, cool.
That's great.
I'll send
Okay.
you an email. Thank you. Have a nice
Brilliant.
day.
Okay. Yeah, thanks, Jess. Yeah, see you.
Bye.
Bye.